And how can we know if people is asking something for the chat?
They writing. I don't esce la notifica quando parlano. Ok, now we are streaming.
Commenting.
Ah, okay, here we go. These are the comments.
Okay, so
Okay.
maybe we can keep
So-
this open and that's all.
Yes, but you have to present
Yeah.
PowerPoint. Okay.
It's here.
Okay.
So they see what there is in the screen.
Yes, now we are completely live.
Okay. So please make a try to see if you can see the streaming probably.
Okay, yes, it's good.
Okay.
It's good.
Is working?
Yes, it's perfectly working.
Okay.
Yes.
Great.
And microphone if you want. Or,
I open this. I don't know if you can hear me in the streaming if you are connected.
well, we are connected and it's working.
Okay. So good morning, everybody, for the people present here in Napoli and the people online. For the people online, I hope you can see the streaming well and listen me well. If you have some problem, please let me know. Okay. If you have some questions, you can write the questions in the chat. So for today, we have a tutorial on the my project. The idea is that we are going to work on the malleability facilities we have in Admire. In Admire is a European project. My name is Jesus Carretero. I am the project coordinator. This European project is part of this Euro HPC 2019 call. In this call, we have 13 projects, and we have especially 2 projects that are devoted to study the input-output things in large-scale computers. Okay, so one project is Admire, that is here, and the second project is IOC, that is another consortium, but basically now we are cooperating together. So the goal of Admire is to enable action based on data, but one thing that is important is that we are based on runtime. We are not doing things like profiling offline and doing things post-mortem to optimize the starting of the application and things like that. We also have these facilities, and IOC is more focused on those facilities. We try to work with the data that we are having in runtime to optimize the I/O and also to provide malleability to the applications, as we are going to see, applications and file systems in the system. Okay? So the main goals of Admire are to basically create an active I/O stack based on a doc file system and operations like data in transit and data in situ, to adjust the computation to the needs of the applications. Okay? Right now, this is still a problem for many years. The I/O systems in the large-scale HPC systems are very rigid, so you deploy the system, typically parallel file system, and you cannot do anything. So people, with the increasing of data, there are many problems now, because the I/O is becoming every day more and more a bottleneck, not the CPU. We have a lot of power now for computing with CPUs, GPUs, and all the FPGAs and all the accelerators you can imagine. However, basically for I/O, we are still like with the same software stack we have 30 years ago. Okay, we have been providing more facilities to accelerate I/O. We have now non-volatile memory, which is nice. We have SSD flash devices, and we try to optimize the I/O doing basically caching on these devices. But in any case, this is not enough, because the way of making the I/O is still the way we were making I/O 30 years ago, and we saturate the I/O channels and everything. And then we are increasing a lot the number of processes and the CPU capacity, computing capacity, but we don't have the same increase in the I/O thing. So in the I/O storage. So the computing capacity and the I/O storage capacity is every day more unbalanced. Okay. In the next, the first supercomputing now in top 500, what they have this is that they have provided basically several racks full of SSDs and non-volatile memory. So what they do is that do the I/O on those racks, and then they move the information to the disk. But in any case, this capacity is fixed. Okay. So what we want to do in Admire is to have scalable solutions that can fit the application need. So basically, what we try to do is adjusting the application needs when we deploy the application first and then when the application is running, okay? So we try to do that with two things. Ad hoc file systems on the one side for I/O, covering several kind of devices, and then also malleability when we are making computing, okay? So the idea of FlexMPI is that we can collect information from the system and the applications dynamically on runtime. So we need a very active, very powerful monitoring systems. And all these powerful and active monitoring systems are collecting the information from the system, from the application, from the I/O devices, every place we can imagine in the computer. And we store all this information and provide that information to one device, one component which is called the intelligent controller. This intelligent controller basically is cooking all the information, analyzing the information, and trying to provide the decisions to make CPU malleability and I/O malleability. We also have another goals with this I/O controlling. The I/O controller can also, for example, limit the I/O bandwidth of some applications that can be very greedy, or can desynchronize applications that are providing I/O collapse due to synchronous operation that is very typical in checkpointing, okay? So the idea is that we have this intelligent controller collecting the information, cooking the information, making data analytics, and then the intelligent controller sends commands to several components in the software stack of the system. First, ad hoc storage system, ad hoc file system that we are developing in the system. Second, we send decisions to the resource manager to provide malleability in the supercomputers. In this case, in this project, we are working with SLAM, as you are going to see, because it's very, very popular in HPC centers. Now there is a new version of HPC scheduler that is, I would say, it's a kind of evolution of SLAM, but it's still experimental, so we are not showing it here. But the new feature of this new scheduler is that you can change the scheduling policy, providing that scheduling policy for the application. And this could be very interesting for our project, but we are not still there. We have also one I/O scheduler. This I/O scheduler is being developed by BSC and INRIA, also UC3M partners. And the idea with this I/O scheduler is that we can adapt the ad hoc storage system dynamically, we can control the data locality, and we can also do co-scheduling of HPC computing and data-intensive application. Imagine, for example, that right now when you make a resource allocation in one supercomputer, if you are using the resource manager, basically all the resources are given exclusively. So you are allocated 3 nodes, all the 3 nodes are for you. Even if you are not using the nodes, maybe you have 48 cores and you are deploying only 20 processes per core. Because people say, okay, I know my application, I know what I do. However, this is not always true because at the end, the effective usage of the computer is very low, actually. 15%, 20% in some real-world studies in large supercomputers. If you consider the money that we spend in buying the supercomputing and the electricity we spend, this cannot be allowed. So in such cases, these I/O schedulers will allow to overlap, and the resource manager will allow to overlap applications doing different things. For example, mixing very aggressive CPU application with very aggressive I/O application, okay? So that we could share the resources and optimize more the use of the computer. And at the end, we have also some operations related with the backend file system. What is the backend file system? The backend file system are the file system we have right now. We are working with Lustre and GPFS, okay, because they are basically the parallel file systems we have in the supercomputers now in computing centers. But now we are also starting to work with BGFS that is installed in one cluster that we are using in Torino. So we are going to have a good landscape of backend file system. And the idea is to see how do we use this persistent data layer efficiently and integrate this persistent data layer with the global monitoring and control. So we have now ad hoc file systems that can be deployed with the application, see that we a little changed the role, and now for us the backend file system is not the primary ending of the storage, but it's a kind of archival thing. Okay, so we are a little changing the paradigm, working with the ad hoc file systems massively, and then depending on the policies, dumping all this, flashing all this information to the backend file system. That allows us to use massively, for example, bus buffers in Lustre, or use very aggressive cache of the GPFS file system client, BGFS file system client, and also it allows us to control quality of service between the applications and the client. That is something that today we cannot, it cannot be done. So what is the idea of the Admire? What is the process? The process that we have applications running in the computer, several applications, all the applications theoretically. For the purpose of this tutorial, we divide the applications in two categories. One is the categories of the application that declare to be malleable, and the other is the categories of the application that don't declare to be malleable. But for the purpose of the I/O, we apply the solutions to all applications in the system. Okay? So we have the applications running, the applications are requesting resources, and we are monitoring the application. And this application, this information that is being monitored, is cooked in the intelligent controller, and we are execute several performance models at the same time, depending on the requirement of the application, depending on the hints of the capacity. We have simple performance models to predict the behavior of the application in a very short time. We have more sophisticated performance model based in tools like XtraP from the University of Boston. And now we are developing predictive application model based on Markov. And the idea with these models is to help the intelligent controller what is going to be done, what is going to be the behavior of the application in the next time. So if we see that one application is, for example, needed more resources because CPU is exhausted, memory or I/O is very limited by the situation of the application right now, and we have more resources available in the computer, we can decide to expand the number of nodes devoted to the application, increasing the number of processes, or we can decide to deploy a larger ad hoc file system for that application, increasing the size of the file system. Okay? So what we are seeing today is the way of expanding the nodes and the processes of one application dynamically while the application is running. Today we are going to see only MPI-based applications, okay? Because MPI-based applications are the problem here. Most people use MPI, and we are trying to provide solutions for MPI. But the same solutions are valid for non-MPI. Actually, it's easier to do that for non-MPI-based application, okay? So we have the same kernels running for non-MPI. But MPI is very tricky because you have to play with communicators. We are going to see, okay? And also here we have the ad hoc schedule file system deployed optimally at the beginning using the profiling information we have from the application, from previous execution. And we have the I/O scheduler here also doing data staging, very aggressive data staging to the backend file system. In our case, primarily Lustre. So this is the architecture we have in our system. As you may see, we have the intelligent controller with one I/O co-scheduler, malleability manager, taking decisions to make malleability for CPU and I/O. And we have this module to make analytics of the monitoring data and running the performance models. We are interacting with the job scheduler, in this case SLAN, but could be another, okay? We have SLAN in the project, and I think it's the major one in any supercomputer. And we have the ad hoc storage system and the backend storage system. Okay? So the interesting thing here is that we try that the application do not work directly with the backend storage system. Okay? We try that the application always use our ad hoc storage system because we can manipulate our ad hoc storage system, file systems, and we can adapt the behavior to the backend storage systems. If the application goes directly to the backend storage system, then we cannot do anything else. Okay, so we have several ad hoc file systems, and we are providing interfaces for MPI-IO, and we are providing POSIX libraries that intercept the calls from the applications, and the usage of this ad hoc file system is transparent for the applications. Okay? Applications don't see this ad hoc file system at all. The only thing they have to define is the path of the files they want to use, and that's all. The other thing that we are playing with is the CPU, the computing malleability. And in this case, as we are going to see today, we cannot be so transparent as we would like. Ideally, if we have one legacy application, making malleability should be transparent, but it is not possible. Why? Because in one malleability operation, we are going to change drastically the shape of the application and the data distribution. So we have to know basically that we are in a safe state, that we can do it. Okay? So as you are going to see here today, basically we have to include in the application things to start the malleability region and stop the malleability region. There is a kind of criticality region that allows us to modify the shape of the application without breaking everything. Okay? So the connectors of the applications with the intelligent controller and with the ARMine framework is one library that we call the application manager that you are going to see today. And this application manager basically includes the facilities to allow the application to call the interface, the intelligent controller to say, okay, I want to start malleability now, I want to stop malleability now, and also to provide hints to the application. And also to start monitoring and end monitoring. The start monitoring and end monitoring calls are only for monitoring that application. Below we have monitors running in the system and global monitors that are collecting information, even if the application says something or not. Okay? But if we start the monitoring, we are collecting more metrics that are relating only to that application. This is what we call the application manager. The application manager you are going to see here today is an evolution of one solution we have at UC3N, which is called FlexMPI. FlexMPI has been running around since 2016, 2015, and it allows to provide malleability for some cases of MPI applications, but not in direct interaction with the resource manager. Okay? We were doing other techniques. Now we have generalized this FlexMPI application manager, and we are also providing connector with the resource manager, with the SLAM, and we are providing interfaces for not only for C or C++, we have now interfaces for Fortran that are running, and we will have interfaces for Python also, because there are the use cases we have in the application. This is the structure of the intelligent controller. And here you can see the system analytics module, the application analytics component to analyze each application that is running, and we have the information stored in one Redis distributed database, which is Redis because basically it's very effective and can be distributed easily to avoid bottlenecks. And then we have all the communication with the system itself, the runtime communication controllers. So we have the SLAM manager to talk with SLAM using RPCs. We have the monitoring manager to get information from the monitor system and provide the performance model, the performance model in the malleability manager. We have the scheduler, the ad hoc file system, and the integrated intelligent controller scheduler. So see that we have all the main controllers here. I don't want to be very insistent on some points. If you have some questions or comments, we can give you more information, okay? So how do we execute the process malleability? For the process malleability, we may have two solutions, basically. One is what we call internode malleability, and the other one is what we call intranode malleability. Internode malleability is the solution you're going to see here today. So basically, when you request more resources, you are provided with more nodes. Okay? Intranode malleability will be also provided, and the idea for intranode malleability is that if you are requested resources and you have resources spare in your nodes, you will be allocated those resources. Okay? But it depends on the configuration that the system administration provides on the resource manager, more specifically on SLAM. So when the application starts the malleability operation, this malleability operation arrives to the intelligent controller. The intelligent controller studies the request of the application. In the application, we may receive hints saying, okay, I want to have 10 more processes, 20 more processes, minus 10 or minus 20 more processes. This is not only a question of spawning the application. We can also reduce the application, okay? And we analyze the request, and if the request can be provided, can be satisfied, we set the orders to the resource manager SLAM to modify the application, okay? Modifying the application in the number of processes is complex. However, we have another question that is not easy here, that is data redistribution, data reordering. Depending on the state of the data managed by the application, if you change the number of processes, you have to change the shape of the data redistribution. In many HPC applications, this is easier than we think because at the end, they do repetitively, they do collective operation to do reconciliation like all-to-all, all-gather, broadcast. Many of those applications do that, okay? So that application reorder the data very easily. If this is not the case, in the environment you are going to see today, we have some operations to make data redistribution for regular distribution, irregular distributions, some applications like Jacobi, conjugate gradient, things like that. But if the data redistribution is more complex, the application has to do it. We don't have a solution today for all the data redistribution, we don't know. So what is the final idea? The final idea is providing the application one way of plugging the data redistribution, sending a function or a policy to make data redistribution and execute this data redistribution. The malleability manager receives the request, and depending on the system information and depending on the data coming from the application, execute the several performance models we may have, depending on the time we have to answer, on the deadline requested to answer to the request, and looking at the performance model, provide a scheduling solution for that application. Initially here we are talking for one application. Now we have one discussion open, is that if we should affect several applications at the same time. Okay, so imagine that we classify the application malleable and not malleable. If you are a malleable application, you will say, this is the minimum number of resources I need, this is the maximum number of resources I need. So while you are in this window, somehow you accept to be changed, to be adjusted to the budget we have. So now, not only in this project, in other projects, and with people in US, we are discussing if it is better to have a budget of resources for this kind of malleable application and just allocate the resources as needed for several applications at the same time, okay? We are working with other projects in Munich and other projects, and basically there is some initiative to provide some modifications, extensions to the MPI standard to provide this kind of things using MPI session or PMPI modifications, for example, some other things, okay? Right now we are talking about one application. Well, this is the performance model thing I was talking about. And what about the I/O malleability? I/O malleability is very interesting because I/O malleability is not fired by only for the CPU needs. I/O malleability can be fired by the intelligent controller itself or by the application. How can we find the malleability in I/O for one application? Imagine we can deploy the ad hoc file system, and we deploy the ad hoc file system with 20 nodes. And we see that the usage of the bandwidth is very stressing, and the application is bit delayed. The intelligent controller can take the decision of increasing the ad hoc file system deployment without saying anything to the application, or decreasing, okay? Again, don't always think, because people say, okay, I'm doing malleability, I am always going to grow. No, you can also shrink, not only expand, okay? So, in this case of the malleability for I/O, the malleability is made through the I/O scheduler, And this IO scheduler is already running. We have a first version. And we have also a version of the data stages to send information from the ad hoc file system to the parallel file system very aggressively and very efficiently. Okay? One thing that is interesting here is that we may have several types of ad hoc file systems. We are not going to see this here today, only malleability, but we may have several, actually we have several types of ad hoc file systems. All of them allows the deployment of elastic storage system, file system, but we have now actually four kind of ad hoc storage system. One is the Gecko file system. That is, Gecko is a well-established now file system. It's still in version, prototype version, but it's deployed now in several places. In here, we have a file system that is based basically on using heavily bus buffers file systems from the backend file system. All of them are deployed dynamically when the application starts. We have Hercules that is only in memory. We are deploying one in-memory file system only. In-memory doesn't mean run memory. We have non-volatile memory. We will deploy it in non-volatile memory also. And we have Span that is also an ad hoc file system that is based relying on having local storage system. Span is very similar to BGFS. However, the management of metadata is more efficient in Span. Actually, we have made some comparisons now of Span and GPFS, for example, a BSC, and the performance is much better than the GPFS. And also we have one distributed object store that is data clay that is coming from BSC. This object store is also well established, and the idea is to provide people storage from the main memory object to the parallel file system without fitting the block interface or something like that. The main problem with data stores is that we have to, if we do that, we have to reshape the way of the interface of the application. Instead of having one read-write like in POSIX, we have things like get set with key value parse. Okay? Here in Hercules, we have also POSIX and we have get set interface. But right now we are not using it because we don't have any use case in HPC right now using get set in our project. Doesn't mean that there are not these kind of things, okay? And as I said, right now for POSIX, the application of this ad hoc storage system is completely transparent. We are intercepting the calls, which is the typical strategy you do everywhere, and we can deploy the systems. Here we have some examples of the ad hoc file systems we have. I don't want to be very spend a lot of time here today because we were losing a lot of time. Basically, this is the solution in Gecko. You can see that internally are different. This is the solution in Gecko. This is the solution of deployment we have in Hercules. Okay, and this is the solution we have in Span. See that even if all of them provide a similar functionality, the way of deploying the parallel file systems, ad hoc file systems, and the behavior is different. For the users and for you, if you are interested, we are providing now a script to deploy these systems with the applications. So using the system is very easy. Okay, we are now integrating all the three file systems so that we can start one or another just by including something in the starting script. The name, one hint, we'll see. So if you want to test, not right now, but in a 1 or 2 months, probably these kind of systems, they are to be available, and it is worth to do it because you can enhance the I/O of the application a lot. We have now very sophisticated monitoring system. One partner of the project is Paratools. Paratools has a small company, an SME in Europe and US. Is working in Europe, US, and Japan right now, and they have a very sophisticated monitor tools that is called TAU, T-A-U. And in this project, we have complemented these tools with other tools like limitless, for example. That is one monitor that we are deploying at UC3N that is working very well. Okay. So the idea is that we collect several traces here, MPI exporter, strays, ad hoc file system monitors, Lustre file system or other parallel file system monitors, and we, the monitoring manager, collect all the metrics, cook the metrics, and store all these metrics in two places. One is one Prometheus exporter that is very standardized. It's basically a time series interface. And the other one is the Redis database of the intelligent controller. Okay? So this is the base of all the information that we use later to do the analytics. In here, we may have alarms, and these alarms are sent to the intelligent controller to also take decision on malleability. Imagine that you say, okay, I want an application, I want to know if an average, the usage of CPU is below 20%. This kind of things in the malleability manager says, the monitoring manager, send that information to the intelligent controller. Again, I want to know if one of my CPUs, one of my nodes CPUs are over 90% continuously, or if the memory is overloaded, or if the energy is very high. So we can set up these alarms as hints, and the system is controlling the alarm and putting also this alarm in place to take decisions. Here you have one example of the output we see in the web. So you see that we have a lot of information, not only for the application. That is something that there are several monitors, good monitors, to see the application in detail. We have information for the application and for the system. Okay, so that we can play with the system information. The analytics model, I said, is running several performance models together with the malleability manager and executing a machine learning tool to predict the things that may happen in the analytics module. And this is critical to take decisions, okay? Not only for traditional schedulers, but also using these performance models. We have now some models that are mimicking the behavior of the informations. We have model for CPU and model for I/O right now, okay? This is one example of CPU and memory for one real application. This is one kernel, not a very large, complex application, but this is for one real application. See, we have memory, CPU, and the network, and this is the prediction we are making right now with our models. So you can see that we can fit very well the behavior of the application, so we can predict if the application is here, we can predict what the application is going to do here, and we can take decisions. Okay? So see that, for example, this application is using the net very poorly, is using the memory over 50%, more or less, and the usage of CPU is very is varying, but you can predict it. Basically, see that the usage of the CPU is very, very low most of the time of the application. So this is a typical application that is running most of the time serially, and then from time to time you have something like a blast or kernels or something like that doing some aggressive application. Many HPC applications are like this. So most of this time, all the resources are under use. You could use these resources for other applications or to reduce the number of CPUs in this application without any problem. Okay? So this is the kind of decisions we want to take. Also for the I/O, we are collecting traces. Actually, we have now an initiative with other European project use cases, and we have set up a place. We are collecting I/O traces that will be made public in a short time, probably. And we are using Darsan and other tools to collect the application. And the idea here is to know what are the applications doing, not only one application, several applications, and being able to mix the behavior of the I/O loads of the application that are started in the supercomputing at the same time. So some example of the traces we get using Darsan, for example, is this. This is the traces of NEC 5000 application. That is one of the use cases we have. It's a very large application, basically, and the main source of I/O in this application is coming from checkpointing. This is not surprising because, again, many HPC applications are like this. So you see that the usage of I/O is practically nothing during a long time, and then you have suddenly you have a burst of I/O that is very intensive. Okay. If you have the traditional file system, you have to cover all this situation with the parallel file system, which is not very good. And with the ad hoc file system, you can cover very well these spikes without reducing the application performance. Okay. And what about interference? When we are playing with CPU, I'm playing with my computer, with my resources. When I play with I/O, I play with the system resources. So if I am writing here in my application, I can know what my application is doing, but I don't know what the other application is doing. Okay? So traditionally, in MPI, for example, if you use MPI I/O, people try to do views in the application, and then in the MPI I/O modules, they try to do staging, sieving, other techniques to avoid these kind of problems, to optimize the channel. But if you have interference because several applications are trying to do the same at the same time during the same device, you cannot do anything. In here, we can do things because we have the control over the ad hoc file systems, and in intelligent controller we know what is happening. So we can apply, using the I/O scheduler, quality of service politics, as I told you, to limit for example, the bandwidth of the application writing and stopping the application, or to defacing applications to avoid I/O synchronization of operation at the same time and collapse the system without any reason. Okay. And finally, we have several applications use cases in our project. In other projects, there are others that we are starting to cooperate now. We have basically one weather forecasting application that is coming from Raffaele here, we'll see now. We have molecular dynamics, turbulence simulator. There's a Fortran application. This is a workflow in C++. And then we have two applications that are related to heavy machine learning techniques related to imaging. One is related to satellite images for continental land cover in Jülich, and this is from brain upper resolution in Postman. And then we have one use case that is not so HPC oriented, but is very interesting because it's pure AI. It's basically an indexing application that is managing millions of small files. We need to manage, here we have not so many files, very large. Here we have millions of small files that we have to process. We need a lot of memory and we have to index. So with all these processes, we can cover very well a different landscape of applications and be sure that the applications are fitting, okay? So see that we have a design, co-design life cycle 9. Now we are profiling the monitoring, taking the information, putting recipes to filter to analyze this application, getting the data from the instrumentation that is being processed and collected according to the recipes, the metrics that we are interested in. We pass this information to the system, feed the extensions, take the decisions, run the execution again, and see the result, and go back, and go back, and go back. So we are not doing the solution and just giving the things to the application. Okay, this is the solution, use it. They tell us what they want, the need they have, and they cook the solution, provide the solution, execute, collect the information again, and we are continuously doing this kind of optimization cycle. Is one iterative cycle that is called co-design because we are doing both things at the same time. And that's all on my side for the introduction of my project. If you have some questions, I would be happy to answer them. If not, we start with the malleability facilities. So for the people online, if you have some questions, you have to write the questions in the chat. So I don't know if I see the chat very well. Let me see. Okay, I don't see anything. Questions? No? Okay. No. Yes.
In order to scheduler applies every slice of time, every one?
No. No. You mean for the malleability scheduler?
Yeah, no,
No.
every second, every...
No. We only apply malleability operations right now on demand by the application. So the application can control, imagine that you have an iterative operation.
And if the application changes its behavior, still, if the application has a different execution phase and changes its behavior, the schedule remains the same.
If they don't say anything, yes. I mean, we don't want to be we could be more aggressive, and we can do it. But for the application programming is very...
Very stable.
No, they are not very happy if you start manipulating the application without them to know, because they think, okay, I have my application is very well designed, I know what I need. So basically right now, as you are going to see, they are requesting, first they declare if the application wants to be malleable or not.
But you can have several applications, multiple applications
running
at the same time.
Yeah, we do that. We not only schedule one application, we consider all the applications running at the same time.
So if another application comes in the system, so you reschedule, no?
Yeah. So imagine that you have 4 applications that said, okay, I am malleable. And you see that even a new application arrives that is also malleable. And you see that several applications have resources that are not using full. And you can do something better, even reducing the resources. We can allocate resources to the new application, stealing resources for the other applications. But we cannot do it at once because we don't know when the application is running. I mean, we cannot control. This is a distributed system. We cannot control the thing with the clock. So if the application, next time the application said, okay, start malleability, we will have the new reschedule prepared and we will reset the application. But if the application do not do that, we don't do anything. We are pure servers. We are not proactive. Maybe in the future we can be proactive, but not now.
Last question, which network topology do you have?
Right now, we have several network topologies because we have several computers. We have been playing in BSC. They have, if I am not wrong, they have a FAT3 with an Omnipad. We have now tested in a cluster in Torino. They have something similar. They have FAT3 with Omnipad. In Jülich, I think I'm not sure the network configuration they have. But basically, all of them are playing with some version of InfiniBand. Yes? Mellanox, but I don't know if it's a FAT3 or Torus or I don't know.
Thank you.
Welcome.
Sorry, one question.
Yeah.
So when you do malleability, you change the number of processes to change the application, and then
For malleability for computing. If we do malleability for I/O, we change the number of processes in the ad hoc file systems.
Okay, no, for computing.
Yeah.
So in MPI, when you change the number of threads, it's
Threads,
processes,
you mean? Yeah.
Okay, so then how does synchronization work? Because, for example, I know with OMP. OMP, when you are in a parallel region, you have to wait because you cannot interrupt. So if you change dynamically when there are many processes, then once you will have something like synchronization issues or data. So how does
You are going to see today. It's all the things related with MPI synchronization with several processes are very tricky. Actually, we play heavily with all the MPI communicators, heavily. And actually, there is now one proposal to, as I said, to do this like a standardized with MPI sessions and PMI operations below, PMIX. Basically, you have to arrive to some synchronization point. You cannot do miracles here. You have to arrive to some synchronization point. So when we make the start malleability and the stop malleability, basically you are saying to our system, here you can modify my program. Because I know that I'm going to be stable.
okay? So the applications need to be changed or instrumented.
You have to include.
For instance, you cannot get an application application, an MPI application, and apply malleability, you have to change it.
You have to include 4 or 5 instructions if you want to use our system.
Okay.
If not, I mean, you can be aggressive without doing anything, but the risk of breaking the applications is very hard. It's very hard. In some way, you have to tell the application, I'm going to modify you.
Okay.
In this case, we tell the application, tell us if we can modify you. We could do the other approach. That was the first approach was, okay, send one command in one of these control points to the application and say, I'm going to modify you. Both approaches are valid. I mean, you can be push. I mean, you can be server or client. You can you can be the active actor, or you can wait. In here, we have the decision taken somehow, but if the application doesn't ask for the decision, we don't modify anything, because we assume that the users are the main role here. Right now. Maybe in 1 year, we don't know. We have to see this co-design.
Okay, thank you.
Well,
We are going to see some of these points right now,
yeah.
and you will be able to test these things in the afternoon session.
Yeah, in the afternoon session, you have seen the documents. You are going to see there are 2. You can download if you want to test one virtual machine with a virtual cluster, and you can test the samples and the solution. So I give the floor to Alberto Cascajo, that is going to introduce you to the malleability things, and then in the afternoon, Alberto and Javier Fernandez will run the demos. Okay. Thank you. No, it's better.
Well, I'm going to start with the theoretical part of this session, which is describe what is FlexMPI and describe its internals. In order not to waste a lot of time, I will pass some point. This is the outline of the presentation, which consists on basically describe some interesting points. The first part is an introduction. I will describe the environment, the HPC environment related to the malleability and the dynamicity of the systems. And then we go going deeper into the FlexMPI source code. Finally, I just present some use cases and the materials for the next session. And what is dynamicity and what is malleability? In general words, malleability is the ability of an entity to adapt its resource usage on demand. Dynamicity basically is the ability of an entity, which can be a system or a process or whatever, to adapt its performance behavior to deal with changes in the workload. So dynamically and malleability are related concepts in HPC, but we can consider malleability as a subcategory of dynamicity because it is a special a use case or a part of the dynamicity. As Jesus has said, there are 2 different systems from this dynamicity concept that are proactive systems and reactive systems. Proactive systems are those that can predict the potential future events in order to anticipate a decision. If they typically use system monitoring and prediction algorithms in order to do these things. And reactive systems is the opposite. If they detect an event, they react, providing a new scheduling, a new decision, and reconfiguring the application and the system. So basically, proactive tries to advance decisions before an event occurs, and reactive take decision just when an event has taken place. Also, it's important to note the different type of jobs we can find when we are working in dynamic environments, which are rigid, moldable, evolving, malleable, and adaptive jobs. The first type refers to those processes that always have the same configuration. Configuration means the same amount of resources, the same allocation resources. This is the most basic jobs and has the same configuration in every system. Malleable jobs can be deployed with different allocation resources. So you can specify a wide range of acceptable resources, and the system could launch your application based on some of your requirements. Evolving and malleable jobs can run with different resource allocations, but they differ from the previous ones because they can change their resource allocation in runtime. So you can see rigid and moldable with a fixed site in their life cycle. However, evolving and malleable can expand and reduce their resources in runtime. Finally, we have a category which is adaptive, and we use it to include both evolving and malleable jobs. If an application can act as evolving and as malleable, we name it adaptive. So just a comment regarding this point. Note that having dynamic processes do not make sense if the system can't support this dynamicity. So we need to perform these malleability features not only in the application, but on the systems. So now we're going to see what are these jobs, how they run. As I have said, rigid jobs are those that have a fixed site, and they are the most basic. In this case, the resource allocation remained constant during the whole execution. Malleable jobs has the same allocation over the execution, however, they can be executed with different resource allocation, with different sizes of resources. In contrast to the previous types, evolving and malleable jobs can adapt their resource in runtime. So, evolving jobs can adapt their resource usage on demand based on external decisions. Okay, so in this case, for example, evolving jobs start with their execution, and then the resource manager tells the application, please reconfigure yourself. So, evolving jobs accept decisions from the system. Different from this, we have malleable jobs. Malleable jobs, as evolving, start their execution. However, is the application who decides when and how to reconfigure. Okay, it's the difference between evolving and malleable. In this case, malleable jobs have mechanisms to monitor their performance and to take the decision. Okay, it's the difference with the previous one. Finally, adaptive jobs, as I've said, is a group that we have defined in FlexMPI to include those jobs and applications that can perform evolving and malleable actions. So, what is the malleability of an application? It's the capability of adapting the size of an application in execution time. There are two types of operations, an expansion and a reduction. When we want to perform an expansion, we use spawn function, so we spawn the processes, and the reduction is the opposite. We can identify three main benefits from the user point of view. The first one is that the application can improve dynamically the performance if the resources are available. Then the processes can adjust their load in runtime. If, for example, if the load is unbalanced, we can use FlexMPI in order to balance this load. And if an application has compute-intensive phases, and then, as Jesus has said, start an I/O phase, for example, they can free some computational resources in order to allow other applications to use it. If I don't need computational resources because I'm doing I/O, maybe I could free these resources for other applications. So among the benefits of using malleability, both at computation and I/O levels, we can highlight the following ones. Applications can increase and decrease their allocated resources in runtime depending on the current status of the systems, both for computing and I/O resources. For the Admire project, we integrate Slurm as a resource manager with FlexMPI because it is one of the most used workload managers in HPC environments. And we allow expansion and reduction of the processes in coordination with the Slurm allocator without the necessity of modify Slurm. So we work with the current version of Slurm. In order to include malleability in the applications related to the Admire project, we provide a set of function calls that the developers should use in their codes to integrate these malleability features, and this coordinated with the intelligent controller and the resource manager. And the objective is not to modify a lot the legacy code. We try to do it in the best way for the developers. Additionally, once an application integrates FlexMPI and has malleable features, FlexMPI provides a set of pattern redistribution for the data, trying to avoid the manual data redistribution for the developers. The point is that this data redistribution depends on the data, the application behavior, and obviously how the developers want to do it. Sometimes there are conditions that we can't manage, and developers should do it instead of let the system do it automatically. Not all the application can benefit from this feature, at least right now. However, as Jesus has said, we want to extend the implemented patterns and let the developers to include new patterns for this data redistribution. So, as a challenges in the field of the malleability and dynamicity in this context, it's important to implement the required changes in the software stack in an efficient way. We need to support all these malleable features without interfering with the rest of the components. It is crucial. Adding dynamicity to the traditional system increases the complexity of the system itself, because the jobs and the resource allocation now are not static. Now these jobs and their behavior is dynamic. So as the scheduling is more complex, we need to monitor the system, and this monitoring and modeling becomes crucial. As monitoring becomes crucial, we also have the necessity to predict the behavior of the system in more complex ways. Imagine that in static systems, we can monitor the resources and predict their behavior with more or less accuracy. However, in dynamic systems, we are including dynamic variables in runtime, which change a lot the scheduling decision, which change the behavior of the applications, and we need to take into account all of these features. So it's something, it is a challenge to design these schedulers and predictors to work in these environments. Last but not least, one of the biggest challenges is to change our minds. Developers should focus on the efficiency of the systems, providing different acceptable resource allocation for their jobs. Considering efficiency, for example, we need to focus on the efficiency of the system instead of the performance of the application. That's what malleability makes sense in these scenarios. We have a lot of resources. We can ask for new resources, but we can free those that we don't need to let other applications to leverage them. The main objective of FlexMPI is to provide malleable features to MPI-based applications in coordination with Slurm to allocate those resources. And this is an important part of the Admire framework. So we are working with different teams to provide full implementation of a dynamic system by integrating a lot of tools and a lot of teams. to cooperate, including FlexMPI. Now it's time to explain what FlexMPI is. FlexMPI is a runtime that provides dynamic balancing and performance-aware malleability capabilities to MPI-based applications. It is written in C plus MPI. It is used with iterative SPMD parallel applications. And it consists of a multi-thread library linked to the application that is able to spawn and reduce the processes in runtime. Here you can see the code and the QR. Then I will provide a list of sources to download all the components. However, note that this version is not the admired version of FlexMPI. Okay? We are developing new features, so this version just spawn and shrink the application processes, but does not integrate the Slurm and other components from this project. This is an evolution of FlexMPI since we started it in 2012. It is just something historical. So, FlexMPI provides malleable and adaptive capabilities because it allows applications to reconfigure themselves in runtime. We provide adaptive capabilities, and basically the important part is that we have another component inside FlexMPI, which is the controller, that acts as the internal scheduler. Okay? If you want to download FlexMPI and test in your system, we have an internal scheduler that monitors, schedule the application, and take decisions related to the I/O, for example. Just curiosity. So generally, FlexMPI applications involve three types of function calls. MPI calls are those calls that we don't need to manage or to capture. We use them as they are. MPI wrap calls by means of PMPI interface. We need to capture, for example, MPI init, MPI finalize in order to set up our framework, and specific ADM calls that perform the malleability, registration, data acquisition, etc. So then, depending on the type of jobs that we have identified previously, we have different functionality. Basically, load balancing, dynamic process management, and data redistribution. But FlexMPI can provide different functionalities related to monitoring, computational prediction models, different reconfiguration policies, etc. So it is not just a framework to provide malleability. It is designed to improve generally whatever kind of MPI-based application. This is a flow diagram of how FlexMPI interacts with the processes in runtime in order to expand and reduce the processes. As you can see, basically, we have here application, MPI application with end processes. We are continuously monitoring the application, and if we want, we can expand or reduce the application in one column. If we want to expand an application, we create the new processes, we integrate them in our communicator, and redistribute the data between all the processes. Then the execution continues. If we want to reduce an application, we first redistribute the data between the active processes and then remove all of those processes that we want. This section will show you how we can pass from our MPI code to a FlexMPI code. This is a general overview. Then we can see how to do it in runtime in a live demo. Basically, if we have our legacy code, we have five functions that we have to use to provide this malleability, which are these that are colored in green. MPI commit and MPI finalize, MPI init and finalize are wrap functions, so we can use it transparently. Same for MPI com rank and size, etc. Here we need to register the attributes of the application. and we can set another if we want from the environment. Then it's important this section. We need to identify in runtime which process we are executing. At the beginning of an application, all the processes will be native processes. However, if we spawn new processes, these processes will be dynamic processes. It's a category. The objective is to identify the initialization. Note that the native processes need to initialize everything. However, dynamic processes no. Dynamic processes need to start computing in just one point of the loop, for example, one iteration with certain data, not the initial data. So we need to identify what have to do, we need to identify the requirement for each process. Then we have here the malleable region start, malleable region stop, which defines where the malleability could take place. These are the basic interfaces for integrating the malleability in the application. MPI init, finalize, monitoring service, allow the user to start or stop the monitoring service. Malleable region to recognize, to specify the region for the malleability actions, and the functions to get and set the internal values for FlexMPI. As I have said, FlexMPI was designed for iterative single process multiple data MPI applications. And the main idea was to fix a sampling interval expressed as a number of iterations where the reconfiguration action and scheduling decisions take place. The algorithm decides to make an expansion or a reduction once an application achieves one of these iterations, which are user-defined. The idea is not to check every iteration the possibility of a reconfiguration, because it increases the overhead a lot, and note that the algorithm could say expand, 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 and we don't want to expand every iteration. So we want to avoid these behaviors by including some synchronization points during the execution. In this slide and the next, we are going to see how we integrate in our FlexMPI world the new processes. Once we expand, for example, in this case, two processes, those two processes has their own MPI world. The second step is to create a group for the spawned processes and then merge the ADN com world with the remote com. Now we have a group that includes both the native and the dynamic processes. This is the opposite. If we want to shrink the number of processes, we need to do the opposite. We have here two processes. We get them out. We get two out from our group of the communicator, and then we remove this communicator, this group, and finish the processes. It's the same process than spawn, but in the opposite way. As I have said, FlexMPI provides malleability features to the applications, and it's an important topic for that matter. So this is the architecture. Jesus has described better than me in the previous talk, so I'm going to focus that FlexMPI contributes to some of these components, but today we are focused on the application side. Okay, so FlexMPI is in charge of providing these malleability features to the MPI applications. We can provide a transparent data redistribution for the developers. Currently, not all the applications can benefit of it because it depends on other values. It also includes an internal performance monitor based on the PAPI performance counters that can measure flops, CPU, I/O, and we can use those counters improve the decision making. And finally, it provides a performance model that can be used to predict the performance of the applications under different circumstances. For example, with different number of processes, different policies based on energy or not. We have several configurations. Now I'm going to describe briefly some benchmark and real use cases that integrates FlexMPI. And it's important to remind that the integration is more or less easy, but it also required a redesign of the application to tell the new processes what they have to do. It's the hardest part of this integration. So, as use cases, we have some kernels, which are the Jacobi method, which is a CPU and MPI intensive application. We work with dense matrices, and we have good data locality. Conjugate gradient is more or less the same, but using sparse matrices instead of dense matrices, so the data locality is poorer. And we have synthetic kernels that we can tune to generate different CPU communication and I/O phases, which are good tools to test the systems. As one of a real application, I can mention Epigraph, which is a simulator, that simulates the propagation of the influenza and COVID-19 viruses. It performs CPU and communication intensive phases that depends on the number of infections. And for a year or maybe a couple of years, we are using this simulator to predict the COVID-19 propagation in Spain with good results. We have NEC 5000, which is an open source computational fluid dynamic solver based on spectral element method. This application also performs CPU intensive phases combined with I/O phases due to the checkpointing. Okay. And finally, we have here Wacom, which is a three-dimensional Lagrangian model that is implemented as an evolution of the LAMP3D algorithm, but I don't want to explain it because Rafael, I'm sure that will be describe this better than me. So, in order to finish this session, I want to show you some QR codes. The first one will redirect you to the Admire European project. The second one is the FlexMPI GitLab. Remember that it is not the Admire version, it is a previous one, but you can use it and it runs well. And I don't know if you want to take a photo, we can put them in the booth. And here is the most important. It's the Docker image that we will use in the afternoon session. You need to download a Docker desktop or a Docker manager in order to try this. And it includes all the dependencies and software that we are using, or we are going to use this in the next session. Also, I want to include here, because this is the instructions to generate to compress the tarball, and these are the instructions to create the image of the Docker. So if you want to do it, it's better do it now or during the lunch than during the session, during the afternoon session, because this needs between 400 to 1,000 seconds to generate and start. So this is basically a Docker cluster that creates 3 nodes with 2 CPUs each, and it includes different examples that we can test, and we will show you later how to transform C and Fortran applications into C and Fortran FlexMPI applications, and how they combine or are coordinated with SLARM and the intelligent controller to expand and reduce the processes, providing these malleability features. So this is all for my side. I think that I am on time. I don't know if I'm on time. Well, more or less. So this is a theoretical part. If you want to ask something, yes.
So, a question about how you perform. Sorry. So I have a question about how is performed the spawn operation or the shrink operation. That you saw how you create the processes, and later on, if you want to remove them, they go to MPI analyze, right? Those processes that you no longer need or no longer want. But supposedly, MPI analyze is collective over MPI convert. Doesn't that affect the process that you spawn and load them?
Yeah, it's a good question. The point is that when you spawn new processes, those new processes has their own MPI com world. Okay, so what we do is to create a group with spawn and native processes, but spawn and native has their own MPI com world. So once you remove the spawn processes and make the MPI finalize, the collective calls is for the second MPI com world, not affecting the native processes.
Okay, so you do a spawn operation for each of the processes that you need. When you, for example, if you want to add 2 more processes, you make 2 times a spawn. Or
No. If now actually currently we perform the collective operation. If we want to create 2 processes, we spawn 2 processes. We could do it. We could create a spawn for one and then another spawn with 2 different MPI com world. We do it in the first way, and it's a decision. We could change it.
And also, you mentioned, I don't know if it was you or Jesus, that you were talking about the MPI sessions, to use MPI sessions.
Yeah.
With MPI sessions, as far as I know, you cannot use the MPI common spawn function. How do you base the creation of new processes and add them to the communicator?
This is a decision that we have to discuss. We discussed it before, but we are not agree. We don't agree, everyone. So now everything works. So then we may see.
Okay, thank you.
The problem with the MPI section is that, I mean, it depends on if you start the session with the budget allocated and then you split the session in some group similar, very similar, or you can increase or not the session. And this is not clear right now. I mean, the MPI forum, there are a lot of this. The discussion is just starting, so I assume that can be maybe 2 years until some decision is taken. So we cannot do 2 years because our project is finishing next year. So we are not sure the practical. For example, the code we are going to see here, there is also another group working in, to be clear,
AMPI.
in our project, in also in the university in Grenoble, we are there, we are also Munich, and they propose to use directly PMIX from the application. We don't agree a lot of that because moving the user, the complexity of PMIX is a lot. You have to reshape all the applications to do that. So our approach would be to integrate that inside our codes. So we still keep the interface that is very simple and inside our codes. For the MPI session, I don't know if you were talking about the MPI session.
Yeah, yes.
It's the same. I mean, we can hide the MPI session below the interface. That's not a problem. The only problem here is, where do you get the resources? I mean, and this is now, there's some discussions going on, even in the people having supercomputing centers, saying, okay, we may devote a budget of nodes that are free to do these things. Because actually, because of the scheduler and stuff, they have nodes free. You have nodes that are spare in the system. But only Islam knows that situation. You are not aware of that. So one idea could be to have a kind of bunch node that just only for malleable processes. But only in the approach now in our site is only the users want to be. If one application don't declare to be malleable, we ignore that application completely. Right now. I mean, we have a version of the instrument computing, and there was a lot of controversy there between the users, the system managers, and everything. The user only see their application, and they want the application. System managers see the system, so they want to increase productivity. They want to control all the system. But users are not, I don't know. However, I have to say that in some computers now, most users don't pay. The situation can change with the power consumption, with the prices and everything. And now, many people is wasting resources a lot. It's very clear. You see the numbers is very clear. So let's see.
That's why it's important to change our mind. We need to.
We want to keep the interface for the application easy, because we don't want to mess up the legacy applications a lot. And probably we will include below PI sessions and some other things.
Related to that, the scheduling process is going to be kind of impossible, right? Because imagine that one application reduces the number of processes, and then another one. In that case, Slurm will schedule another application that is within the queue, or
No.
We are calling the Slurm to say, okay, you have to free these processes, or you have to allocate more processes. And Slurm is giving out the number of nodes, and these nodes are removed from the free queue. Went back to the free queue. So in the next iteration, Slurm is going to use it. We don't run the Slurm scheduler every time.
The scheduler is on our side, it's on the admire side, not Slurm is just our allocator resources.
We allocate resources and we free resources, and we send the Slurm queues, and in the next iteration that Slurm is running, it will use those resources.
Yeah, and maybe one application reduced its size, and then it requires more nodes to run on them.
Maybe,
Yeah.
But maybe Slurm scheduled another application and those resources are
Slurm is applying backfill, so.
okay.
But we don't call Slurm to make the rescheduling every time.
Yeah.
We just call Slurm to say, you have resources, give me 3 nodes, 4 nodes. If the nodes are available, we'll take them with the nodes, and these nodes are out of the queue. So for the Slurm, in the next iteration, those nodes are not there. Or they will be there.
Yeah.
We don't reschedule again on the backfilling. We don't want to do that. There is one group in Munich that is proposing to do that. They are proposing to modify the scheduler in Slurm and run the scheduler when you need it. But I don't know. Let's see.
That's the AMPI, no?
This
AMPI.
thing is now boiling. So we still don't know the solution. But for us, it's better to be practical with the application people than be very, I don't know, people think we can also modify the schedule and everything. I don't know. Maybe Slurm can be, as I said, can be substituted in a short time with another schedule. So let's see what's
Can you use the microphone?
So when you request for the new processes in Slurm, are you estimating the time that you are going to use them, or you expand the job so the workload time of the new processes will be the same as the job that is used?
Currently, we don't care about this. We ask for the resources, we wait for the resources while the application is running, and once we have these resources from Slurm, we reconfigure the application. So we don't have to estimate it. We just tell Slurm, hey, give me please a couple of nodes. Once Slurm has given us, we reconfigure the application in order not to waste time.
Because you need the time to allocate the resources?
No, because when you can have a very large application. So the workload time of this application will be very large. And the problem that when we try to use these malleable things is that if you try to allocate for the same time of the application, if you don't have so they have three nodes, but sometimes it's because they are waiting for a big job to enter, and the workload time of your application maybe it's larger than the entrance of this. So sometimes we are losing this time because we can wait, we can use this process just for some time, but we cannot use them because they are as long as it's waiting for releasing resources for this big job.
Booking these resources in order to have all the necessary to expand to execute another application.
We can also release these resources when it's done. And if we are able to predict this time that we are going to use, maybe we can give more information to the plan.
We have discussed this, if I understand, and I have understand you well. We have discussed this before because we know this. We know that if someone wants to execute an application and needs resources, it is booking these resources. So our idea is to leverage those resources until all the needed is available for the other application. So we could leverage to expand an application during this time, and then we reduce the original application and give all the resources to the new application. We have to implement this, but we have discussed it before.
There are two things here. One, the time you need to get the resources.
Mm-hmm.
There is not the critical use depending on the slam. So we have a deadline. If the allocation is not providing this deadline, we just pass the receipt. We don't block application. We just go to the next time they call to see. For the nodes that are free or not, honestly, we are not considering the policy of the plan. We ask the resources. If the resources are given, we use the resources. If the SLAM has a node block for another application, we assume that it will not be provided.
Yes, but
no, you want to.
But in the backfill policy that they have, we can tell them that this is going to be a short period of time. Maybe they are allocating that if we the workload time of the original application, we are not going to get this resource.
Yeah.
And sometimes you want to have a fine-grained adaptation, and you are not able to do because you don't want to lose the resources because maybe you will not get again when you need.
This is again the discussion we have about the owner of the resources. There are two decisions here. One, I'm freeing the resources, but I'm not releasing the resources, just blocking the resources. So someone can use the resources temporarily, but the resources are mine. Okay, so somehow I'm borrowing you the resources, but the resources are mine. The other option is, okay, let's have this budget for all of us, the resources, and they will be shared. So you have to wait. And the other option is the option of, okay, we are going to modify the backfilling, and we have to do a kind of malleable backfilling with all the consequences.
But this option, this last option, is the one that the system administrators don't implement because they don't want to change the scheduling policies. For at least I think they are.
I mean,
Okay, not
I mean, this is like in any company. I mean, you have a way of doing things, you have a policy, and you have to change the policy. And the people managing the situation usually don't like to change because they have something that is working. So let's see. This is changing the schedule is critical here. Let's see what happens. But for sure, for the testing we have made, in many places there are nodes that are waiting for the backfilling, probably yes, and some nodes are not always busy, depending on the time frame. So you can get more, you can release more. There's another question here: is if you release the nodes and the application is using less resources, probably the execution time, the make span will increase. So imagine you told Slam that you are going to use 1 day, and now you reduce resources 30%. Probably your time will increase 2 hours. So we have to modify that execution time also because Slam will kill the application. So the question is, if you as a user said, I need 1 hour, 1 day, and I decide that you need 1 day and 2 hours, again, in this very fast there was a lot of discussions. No, users have always the right to decide. They have priority. So you can modify the make span or not.
That's why we ask for the developers, when they execute their application, give us some allocation that you accept and give us some time stamped for each use case, an estimation. Maybe an overestimation, but we can work with it a bit.
This is something we are starting. We have to test with the user. This is why we have this code design. We have to test in the supercomputing center. But first, we don't want to test the scheduler. We modify the. If we propose them to modify the scheduler,
they won't allow us to execute.
They will say no. So we are being very pragmatic. Sorry.
So now I'm going to install Docker cluster for the next session.
Okay. It's time to
I don't know if I have to stop the streaming or sorry, Javi, ¿vas a usar tu ordenador? Okay, so nothing. Yeah.
Okay, so stop for lunch and start again.